Good morning to all of you. Today we have discussed some basic phenomena about the quantum mechanics. In previous lecture we have studied the wave particle duality, means when the wave travel at that time some scientists told that it having the particle nature, some scientists told that it having the wave nature, means Newton's, Huygens, Maxwell, Young, etc. From this phenomenon, wave particle duality, the wave nature is proved by interference and diffraction. For interference and diffraction. Similarly, the particle nature is proved for the photoelectric effect, Compton effect, etc. Means wave particle duality is present. Then after we move towards the de Broglie hypothesis. On that de Broglie hypothesis, we have proved this last equation, lambda is equal to h upon p, where p is momentum, p is momentum. But for moving particles, if the particles are in motion, at that time the particle having some velocity. Okay, if it is the particle, at that time the particle having some mass also. Due to that reason, P is equal to m into v. Due to that reason, P is equal to m into v. M means mass of that constituent particle, and v means velocity. Okay, velocity of that particle. If sometimes it captures up to speed of light, that is c, is equal to 3 into 10 raised to 8 meters per second. And for the moving particle, we put the value of p in this equation. At that time, what we have got? Lambda is equal to h upon mv. Lambda is equal to h upon mv. And this is the last equation. Previous lecture we already proved this equation. Lambda is equal to h upon mv, where h is the Planck's constant. Planck's constant. Okay, h is the Planck's constant, and lambda is the, we called it as de Broglie wavelength. Okay, lambda is called as de Broglie wavelength, and all of you know that wavelength measurement units. Okay, wavelength measured angstrom unit, nanometer, etc. There are number of measurement units to measure the wavelength. The last equation is lambda is equal to h upon mv. It is the de Broglie wavelength. Previous lecture we already studied that wave particle duality and de Broglie wavelength. But for starting of the quantum mechanics, we need some basic phenomena. Okay, we need some basic phenomena, just like a black body radiation. So what is the black body radiation and how it's work, and how the scientists proved that black body radiations for some shorter wavelength, for some longer wavelength, some black body radiation is applied for the shorter wavelength only. Okay, some scientists proved it for the longer wavelength only, and then after Planck proved it for the shorter wavelength also and longer wavelength also, and they derived the Planck's constant, and it is usually used in number of phenomena. Okay. So today we want to study black body radiation. black body radiation. In this case, firstly we want to know what is the black body. Okay. Firstly we want to know what is the black body. Okay. What is the black body? So, black body, it is the body which absorb all type of radiations incident on it. All types of radiation incident on it. Suppose we have to radiate, for example, 100 number of rays. Okay, 100 number of rays we have to radiate on the black body. At that time, suppose this is the black body. Suppose this is the black body, and we have radiated HM. It is the photon. Suppose these are the 100 rays. Okay. Then what happens? If it is the perfectly black body, at that time it absorbs. It absorbs all types of radiation falling on it. Okay. All types of radiation falling on it. Means there is nothing to lose. There is nothing to lose. Means if we incident 100 rays on it, at that time 100 out of 100 rays, 100 out of 100 rays must be absorbed, or in some cases 98, 98, 99 type rays are absorbed. Means nearly 99.99% radiation is absorbed. Okay. Means in the case of black body, in the case of black body, what happens? Its absorption coefficient. Okay, its absorption coefficient is 1. Its absorption coefficient is equal to 1. For the black body, the absorption coefficient is 1. Absorption coefficient is 1. Also, all the type of rays absorption is there, but all type of rays are emission is there. Okay, means if the black body absorbs all 100 rays, at that time it also emits all 100 rays. Means its emission means its emission coefficient is equal to 1. Means the black body which absorb all the type of radiations and emit all the type of radiation falling on it. Sometimes we have, sometimes there is a question. There is a question related to black body absorption coefficient. Write the black body absorption coefficient. MCQ. There is a 1, 0, infinity, none of these, all of these. Okay. At that time, you must be remember that black body absorption coefficient is 1 and black body emission coefficient is 1. Means you want to remember that the black body which absorbs all the type of radiations falling on it and emits all the type of radiations. Okay. So we called it as black body. For that, here I have to plot one relation between the black body distribution, energy and temperature relations. Means what is the energy and temperature relation on the black body. So this is one diagram. In this diagram, your y-axis must be for the energy and x-axis for the wavelength. Okay, x-axis it is for the wavelength, it is for the energy. Okay, energy and wavelength phenomenon is there. So in this black body, what happens? Here, this plot clearly shows that the what type of radiation is falling on it, what is its effect. Okay, what is its effect on black body? Suppose T is equal to, first T is equal to 2000 Kelvin, 2000 Kelvin. His second T is equal to 1000 640 Kelvin, and this 30 is equal to 500 Kelvin. 30 is equal to 500 Kelvin, and it is its maximum. It is its maximum. Means what happens when we study the black body distribution law? Black body distribution law. In this plot, the first captures T is equal to 2000 Kelvin. Second one captures T is equal to 1640 Kelvin. And third one, it captures T is equal to 500 Kelvin. Different uh, when radiation is incident on the different part at that time, its temperature phenomenon is different. Means if the radiation is falling on it at that time, its temperature is different. Means we got the maxima at different position. If we got the maxima at different position, means it is independent. Okay. What that? The distribution of black body radiation is independent on nature of black body. Means it is not a similar. It is not similar for all the bodies. If the body is different at that time, the black body distribution. Means this is the distribution. Okay. This is the distribution at that time. Distribution of wavelength is different for different bodies. If the body is changed at that time, the distribution must be changed. Okay. At that time, the distribution must be changed due to that. This is called as black body distribution law. Black body distribution law. This is called as black body distribution law. And for this black body distribution law, the black body radiation is independent of nature of black body. Means it is totally independent on nature of black body. If the black body changes, at that time its distribution must be changes. Means for same body, same distribution is there, but the black body changes, at that time the distribution must be changes. So for the distribution, number of scientists studied there for the longer wavelength also. Some scientists study for it the shorter wavelength also. So what happens when someone studied for the longer wavelength, when someone studied for the shorter wavelength? So Stephen proved that one scientist which having the name is Stephen. So we call it as Stephen law of black body. Then Stephen proved that the energy density is proportional to force power of temperature. Means if here draw this diagram, then we here move toward the second thing, Stephen's law. Stephen's law. In this Stephen's statement, what Stephen said that energy density is directly proportional to the force power of temperature. Means he stated that energy density is directly proportional to the force power of temperature. Means it is equal to E is equal to sigma T raised to 4. E is equal to sigma, this is the sign of sigma, okay? E is equal to sigma T raised to 4. We call it as, suppose we call it as equation number 1. Suppose we call it as equation number 1. This is the Stephen law, and sigma is the Stephen's constant. Sigma is the Stephen constant, and it having the value 5.67 into 10 raised to minus 4 Weber per meter cube. Okay, sigma is the Stephen constant, and it's having the value 5.67. 5.67 into 10 raised to minus 8 into 10 raised to minus 8 Weber per meter square Kelvin raised to 4 into 10 raised to minus 8 Weber per meter square into 10 raised to Kelvin 4. Okay, into 10 raised to per meter square, actually per meter square into 10 raised to 4. Okay. Actually, it is not a Weber, it's watt. Okay, power radiation is the power radiation, and it is the watt. Weber for W. Okay. So it is called as Stepan constant. Sigma, we call it as Stepan constant. Okay, this is the Stepan law, and from the Stepan law, what happens? They found some phenomena. Means Stepan found that when energy radiation is directly proportional to the T raised to the power 4. Okay. Once means when the energy is radiated on that black body at that time is directly proportional to the temperature power 4. Okay. Is directly proportional to the temperature up to the power 4. But it is this law, but this law does not tell anything about individual wavelengths. Okay, means this law is satisfactory only for particular wavelengths, but individual wavelength for the particular, it is for the particular wavelength, but this law is not valid for the individual wavelength. At that time, some scientists next to move toward the other phenomena. Their next scientist we call it as wind. We call it as wind. And wind, what the study? Wind established the wind displacement law. Okay, wind displacement law. Wind displacement law. Okay. So what is the wind displacement law? In the wind displacement law, lambda t is equal to constant. Okay. This first phenomenon is lambda t is equal to constant. Means wavelength and temperature, wavelength into temperature, we got some constant. And its second phenomenon is E t raised to minus 5 is equal to constant. Okay. Its second phenomenon is E t raised to minus 5. E t raised to minus 5 is also constant. E t raised to minus 5 is also constant. So all of you know that lambda is the wavelength corresponding to the temperature which having the emissivity E, which having the emissivity E of the black body, which having emissivity E of the black body. And combining these two equations means this equation 1 and equation 2. Combining these two equations using Maxwell distribution law. Okay, we use the Maxwell distribution law to combine wind displacement law, and we obtain some following law. Okay, we obtain following law. We call it as, but its law is only applicable for the shorter wavelength. Okay, this law is only applicable for the shorter wavelength. So, what is its law? Here, I think here. If you have no idea, its law is only valid for the shorter wavelength. And some laws are valid for the longer wavelength, some laws are valid for the shorter wavelength. So this wind displacement law is valid for the shorter wavelength. What is its law? E lambda d lambda is equal to E lambda d lambda is equal to A divided by lambda raised to 5. A divided by lambda raised to 5. A divided by lambda raised to 5 minus beta lambda t upon d lambda. Okay, minus beta lambda t upon d lambda into d lambda e raised to the power, means it is the exponential phenomenon, e raised to minus beta lambda into d lambda. But what is its boundary? What is its boundary? We want to study its boundary. So what is its boundary? It is only valid for shorter wavelength. Means he proved the black body radiation, but this black body radiation only valid for the shorter wavelength. If we call it as equation number 2, E lambda d lambda is equal to E divided by lambda raised to 5 exponential of e raised to minus beta lambda minus b lambda d lambda minus b lambda d lambda. But the wind displacement law is only valid for the shorter wavelength region. So what is for the longer wavelength region? It is not applicable for the longer wavelength region. Means there is a limitation to wind displacement law. It is only valid for the shorter wavelength region. But here we want to study it for the longer wavelength region. Okay. Uh, have you hear my voice clearly?
हो सर.
Have you seen the blackboard clearly?
Yes.
Yes, sir.
हाँ
Listen.
सर.
All words?
हो
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 sir. हो.
ठीक है.
हो सर.
Okay. Mute your mic. Okay. So we called it as A and B. Here A and B are the constant. We called it as A is the constant, and this law is only valid for the shorter wavelength region. Then after that, one more scientist. We called it as Rayleigh jeans. Okay. We called it as Rayleigh jeans. Rayleigh jeans. Okay. We call it as Rayleigh engines. Two more scientists working on that, but there is also limitations to Rayleigh law. Okay, Rayleigh law means what happens? It is only valid for the shorter wavelength. Also, Rayleigh proved it, but there is also limitation for the Rayleigh law. Means what is its equation? They proved it for the E lambda d lambda E lambda d lambda it is equal to 8 pi kt 8 pi kt divided by lambda raised to 4 into d lambda divided by lambda raised to 4 into d lambda. But we call it as equation number 3. If we call it as equation number 3, this is the Rayleigh law. This is the Rayleigh law. And K, you know, this K is the Boltzmann constant. This K is the Boltzmann constant, and this law is only valid for the longer wavelength, but it fails to explain shorter wavelength. Means it is valid for longer wavelength. It is valid for longer wavelength. It is only valid for the longer wavelength. But this law is not applicable. Okay, it is only valid for the longer wavelength. This law is not applicable for the shorter wavelength region. This law is not applicable for the shorter wavelength region. At that time, Planck's proposed. At that time, the scientist Planck proposed a new formula for the black body radiation. Okay, means lastly Planck proved the black body radiation. At that time, Planck proposed a new formula for the black body radiation, and it is valid for the all the equations we have already written here in the all the laws. Means it is valid for the shorter wavelength also, it is valid for the longer wavelength also, it is valid for the Stefan's law also. Means Planck's constant is valid for the all type of wavelengths. Means for the shorter wavelength also, for longer wavelength also. But what is this assumption? It assumes that there is a energy continuously emitted in the form of packets, of energy. Okay, in the form of packets of energy. Means E is equal to 0, epsilon, 2 epsilon, etc. Means E is equal to, means what is called the Planck's law. Okay, Planck's propose that energy having the bunches of energy. Okay, there is a bunches of energy, means packets of energy. Packets of energy means E is equal to 0, epsilon, 2 epsilon, etc. 0, epsilon, 2 epsilon, 3 epsilon, 4 epsilon, dot dot up to infinity. Means there is a bunches of energy. There is a bunches of energy. Means energy cannot travel in the singular form, but always it is travel in the form of bunches of energy. So you know that epsilon is equal to h. We call it as photons. Okay, we call it as photons. And h h nu means photons, and you know that h is the Planck's constant. You know that h is the Planck's constant. Okay, h is the Planck's constant, and he obtained the equation for the energy. And he obtained the equation for the energy. What is this equation? A lambda d lambda is equal to 8 pi hc divided by lambda raised to 5. 8 pi hc divided by lambda raised to 5. And next one is the your exponential cube, means 1 upon e raised to xc on kt, 1 upon e raised to sc upon kt minus 1 into d lambda. Okay, c upon kt minus 1 into d lambda. And this is equation number 3, and it is the last equation. It is the last equation, and we called it as Planck's radiation formula. Okay, this is the Planck's radiation formula. We call it as Planck's radiation formula, and it is applicable for the shorter wavelength also. It is applicable for the longer wavelength also. Okay, means this applicable for the all types of wavelength which is falling on the black body radiations. Which is falling on the black body radiation. Means it is the basically start of the some basic phenomena about the quantum mechanics. Then after one more scientist is there. We also study the problems related to black body radiation. Okay, means you must be remember the all the equations related to the black body radiations. Means E is equal to h nu, or other thing h nu is equal to, you know, nu is equal to cm for lambda. You know, nu is equal to c lambda, and you know is equal to c upon lambda. This c upon lambda, we need this equation for the problem solving purpose also, for the problem solving purpose also. So it is the all about the black body radiation. It is all about the black body radiation. Have you understood? Have you understood?
Yes, sir.
Have you understood black body radiation?
Yes, sir.
Give me answer.
Yes, sir.
Yes, sir.
I cannot hear your voice properly. Speak loudly. Have you understood black body radiation?
Yes, sir.
Yes, sir.
Okay. It is the basically start of the quantum mechanics. Okay. Firstly, this is the black body radiation. Then second thing is the photoelectric effect. Okay. It is already we have studied the photoelectric effect. Photoelectric effect. Photoelectric effect. So, you know what is the photoelectric effect? What is the photoelectric effect? It is, suppose this is one vacuum tube is there, okay? This is a potential is there. Then suppose this is one plate, we apply some potential is here. Okay? So what happens for that plate? What happens for that plate? If suppose it is a vacuum tube, if I have to write here one plot here, one vacuum tube is there, okay, vacuum tube is there, and we have already it having some potential, Okay, already we have some potential. If we consider some photon on it, okay, if we consider some photon on it, so what happens? There is a production of electrons. Okay, there is a production of electrons. Means if this is the plate, these are the photons, h nu. If it's having the potential, if we apply some potential, if this photon having much more larger energy, if this photon having much more larger energy at that time, it produces some electrons and they move towards the air. Okay? With this direction, electrons movement is takes place. You already studied the photoelectric effect. And here, from the photoelectric effect, the famous scientist Einstein proved the photoelectric effect. The famous scientist Einstein proved the theory of photoelectric effect on the basis of wave theory of light, and it is for the particle in nature. From this wave photoelectric effect, what is proved? It's proved particle nature. It's through particle in nature. Okay. In some theory proved that the wave nature at that time photoelectric effect proved that particle nature of light. Okay. Particle nature of light and the photoelectric effect and this photoelectric effect and this photoelectric effect is applicable to various phenomena. It is applicable to various phenomena of light. So here in the photoelectric effect, what happens in the photoelectric effect? After proving the photoelectric effect, Einstein, after proving the photoelectric effect, Einstein give the some idea about the equation. And from this famous equation, energy radiation E is equal to H E. We prove the last equation, energy radiation E is equal to H nu. We called it as photoelectric equation, and from this famous equation, Einstein got the Nobel Prize. Okay, Einstein got the Nobel Prize, and what is the photoelectric effect? It is the ejection of electron from the metal surface. Okay, it is the some metal surface, just like a tungsten. Many of the time, tungsten metal is used. Okay, many of the time, tungsten metal is used. Tungsten, which having the formula W. Okay, W means tungsten. Okay, the ejection of electron from the metal surface. The ejection of electron from the metal surface when light is incident on it. When light is incident on it, we call it as photoelectric effect. So it is the metal surface. It is the photon H nu. H nu means light, and these are the electron emission. And all of these we call it as photoelectric effect. All of this we called it as photoelectric effect. But we only know the definition of photoelectric effect. So what happens in the photoelectric effect? In the photoelectric effect, behind the photoelectric effect, there is some theories. Okay, there is some theories. So what happens? Firstly, H nu, photon. This photon frequency, we need more frequency. Okay, more frequency photon. At that time, only emission of electron is takes place. Okay, we need more photon energy. At that time, emission of electron takes place. If the photon having less energy, if the photon having less energy, at that time, no emission. At that time, no emission. If photon energy is less, photon energy is less, energy is less, no emission takes place. No emission takes place. Means emission of electrons cannot take place when radiation of energy is less. Then second, its energy is independent of intensity. Independent of intensity of incident radiation. Okay, means intensity and energy relation is not carried out here. Okay, Means energy of photoelectron is independent on intensity of incident radiation. Okay, independent of intensity of incident radiation. There is a no dependent on intensity. Intensity independent photon. Okay, intensity independent photon. Energy radiation. Energy radiation is intensity independent. Intensity independence. Then, if the photon incident radiation frequency change, okay, if the photon incident radiation frequency change, this is the first one, this is the second one, this is the third one, fourth one. What is fourth one? If the frequency change, if this photon frequency change, if h nu frequency change, if photon frequency change, what happens at that time? What happens at that time? The energy emission of photoelectrons also change. Okay, means radiation change, energy emission change. Energy energy emission is change. Energy emission is changed. So these are the four observed experiments. Experimentally, these are four observations. Then sometime this photoelectric effect at that time will increase more photon energy at that time. What happens when the photon energy is less at that time? What happens? All of the phenomena explained very well in the photoelectric effect. Then photoelectric effect have then lastly, Einstein proved this equation E is equal to hν. The photoelectric effect having this type of nature also means we move toward the negative potential at that times when we increase the potential we have got this type of graph. We got this type of graph. When we move towards more negative, at that time we also do the photoelectric effect. Uh, uh, Notes available for the photoelectric effect blackbody radiation. I have provided the notes related to the photoelectric effect blackbody radiation also. So it is all about the photoelectric effect, and the photoelectric effect proved that light having the particle in nature, and the photoelectric effect proved that light having the particle in nature. Then we move toward the next quantum. We move toward the next quantum effect. We move toward the next quantum effect. If this is some metal particle, then the incident some electrons on it at that time, what happens? Change it is the change in original and also after its particle nature is proved. If we consider some electrons uh, on the metal surface at that time, some change means some scattering change in frequency is observed. Okay, some change in frequency is observed. Just have to show you it in the PPT form. Okay, I have to show it in the PPT format also. Have you hear my voice?
Yes, sir.
Here, okay.
Yes, sir.
Very good. Uh, yeah. This is the diagram of photoelectric effect. In this diagram, what happens? Light is incident on the metal plate, At that time, collection of electron is takes place. This is the vacuum tube. Vacuum is generated. Okay, and some potential is applied. Some potential is applied to that. It is the experimental finding that there is a no time lag between arrival of light at the metal surface and emission of photoelectron. Okay, arrival of light and emission of photoelectron. When voltage is increased to certain value V0, the photoelectron reduces to 0. Okay, this diagram proves that photoelectron moves to 0. The increase in intensity increase the number of photoelectrons, but electrons energy remains same. Means if we increase the intensity at that time, number of photoelectrons are increases, but all photoelectrons having the same energy. I provided the notes at that time. You got in that note. Increase the frequency of light, increase the energy of electrons. Means if we increase the frequency, I am already told you that if we increase the frequency at frequency below certain critical frequency, no electrons is emitted. Means if we increase the frequency of light at that time, energy of electrons increases. But if we decrease the frequency at that time, at certain levels, emission of electrons not takes place. Emission of electron not takes place. And it is the frequency equation. Einstein proved that E is equal to h0. Now we want to move toward the Compton effect. Compton effect. When monochromatic beam of X-ray is scattered, when monochromatic beam of X-ray is scattered material, from a material, then both wavelength of primary radiation, unfold radiation, okay, primary radiation and radiation of higher wavelength means modified radiation are found to be present in scattered radiation. Means one is the modified wavelength, this is the incident wavelength. Okay, you already observed this. This is the incident wavelength. Means incident on it. Then presence of modified radiation, scattered X-rays is called as Compton effect. These are the electrons we incident on the surface of metal at that time. Scattering of photons takes place. Means h nu dash c sin theta. It is the one scattering, and h nu dash c cos theta. This is the another scattering. This is the electron. This is the recoiled electron. Means there is a change in modified radiation. If incident radiation at that time, modified radiation is changes. Okay, means primary incident we called it as unmodified radiation. This is the primary incident, we called it as unmodified radiation, we incident on it. Then what happens, we got some modified radiation, we got some modified radiation. Then what we have to prove, that it is proved that the radiations which having the particle in nature, means wavelength waves which having the particle in nature, and there is an incident of photon which having the energy E is equal to h. There is incident of photon which having the energy h nu. So it is all about the photoelectric effect, Compton effect and black body radiation. Photoelectric effect, Compton effect and black body radiation. So all of you unmute your mic, and if you have some question, then ask me.